Differential calculus is all about finding the slopes of curved lines. Integral calculus is all about finding the areas between curved lines and the x-axis. This is often called the area underneath the curve. I just want to remind you that differential calculus, finding the slopes of a curved line, is based on the concepts of limits, in which case we take the slope delta y over delta x, and we imagine delta y and over delta x getting smaller and smaller and smaller until delta x became dx, the width of a single point, and delta y became dy, the height of a single point. And so in a very real sense, the slope of a curved line is the slope of a single particle. And I just want to remind you that the width of a single particle is dx and the height of a single particle is dy. And that was a concept that basically had to be invented for differential calculus to make sense. Integral calculus is all about finding this area underneath the line. Chances are, if you have a fancy calculator, your calculator can calculate the area underneath a line. And how it does it is it breaks up the area underneath the line into a series of rectangles like this. And in this case, it breaks it up into 4 rectangles in such a way that it knows the width of each rectangle, and the width of each rectangle is delta x because it's on the x-axis. And then your calculator calculates the height of each rectangle by plugging in the appropriate x value into the given equation for f of x. So if you want to find the height of this rectangle, whatever x value is here, whatever the given equation is, you plug this x value, and that will find the y value, or the f of x, and that will be the height of the x value. And your calculator knows the width of each rectangle, and it goes and plugs in the height of each rectangle, and it can find the areas of all, well, for instance, these 4 rectangles, can find those rectangles just by adding up the height of each rectangle times delta x, because the area of a rectangle is height times width. So for as many rectangles there are, your calculator will calculate the various heights of the rectangle. It has decided on the width of each rectangle. Actually, if you have a sophisticated program, you can actually set the widths of each rectangle. And then what it'll do, it'll calculate this area, and it'll calculate this area, and it'll calculate this area, and it will add them all up. So your calculator will calculate the 4 different areas and add them all up, and it'll say, oh, well, that's the area underneath the graph. So it's this sum of areas that your calculator is adding up in order to figure out the area underneath graphs, if you use your calculator for such a process. How we write this sum in math is using sigma notation, namely that uses this Greek letter sigma. It must be the S sound in Greek because sigma stands for summation, but this is how they write it. This is capital sigma. But if you have 4 sums of 4 different things, and it's very clear where you get the first value, the second value, and the third value, namely by plugging them into an equation, you can write this sum using sigma notation, and that's sigma notation of I equals 1 to 4, and the I goes here. So you're going to plug in x1, x2, x3, and x4 here, multiply them by delta x, and add them all up. And that's what this sigma notation means. And if there's 4 things that you're adding up, the 4 goes here, and if there were 5 rectangles, there would be a 5 here. Summation notation is good because you're going to see in a minute that, notice that if we just use 4 rectangles, the area we're going to calculate is going to be wrong by the area of these triangles, right? It's actually not, the area of these 4 rectangles added up is actually not going to be very close to the area underneath the curve. It's going to be wrong by these 4 rectangles, and now the obvious thing to do is, well, you should use more rectangles. So notice if I use 10 rectangles instead of 4 rectangles, notice even though I have a lot more triangles here, it's still wrong by the areas of these little triangles, that it's just it's just not counting this area. But notice this total area is less than the total area of the 4 triangles when they had the big rectangles. And if I are going to write out this more accurate representation of the area, notice it would take me a lot of f of x delta x's, or I could just use summation notation, like this. And you can see why summation notation is so good, is notice in just a single line of mathematical notation, I can write a bunch of stuff, right? And so, even though it's kind of like the hard part of math conceptually when you get here, remember how much time it's saving you anytime you see this. What really you should imagine in your imagination is all of this. But anyway, it's a quick way to write a lot of sums, and it was important for calculus. I'll bet you can see where this is going. Just like differential calculus, use the concept of limits to get the exact slope of a curved line. Integral calculus is going to use sort of the same idea, only slightly different. But the question is, what would it take? How many rectangles would it take for us to be exactly right? In other words, notice how many rectangles would we have to use to get the exact area underneath this line in this area that I've drawn, and how wide would each rectangle be? Right? And so I'll let you think about that for a minute, so you can reinvent the idea behind integral calculus. Now, I believe both Leibniz and Isaac Newton came up with this idea, and they had to know how many rectangles do you have to use in order to get an exact number for the area underneath a curve. Or what the same question could also be asked: what is the size of delta x to make the area of each one of these triangles? That's our error. That's how much off we are whenever we do this calculation. What does delta x have to be for us to have 0 error? Incidentally, when in the 80s I had this wonderful calculator that would let me calculate the areas under curved lines, and it would ask me to specify delta x, and it was an old calculator. So if I wanted a very accurate answer, I would put a very small number for delta x, but it was a calculator from the 80s, so it would break up this thing into 1,000 little rectangles because delta x was so small, and then it would sit and think for minutes, and it would be computing, and I would have to wait. Sometimes I would wait for 2 or 3 minutes before it would tell me its estimate of the area, because I put in a very small delta x. Okay, so what do you think I'm going to tell you? Pause the video if you still want to guess. Remember, the question is, how big does delta x have to be to get an exact area using this method? And the same question is, the other question could be, how many rectangles do you have to use in order to get an exact answer using this summation method for calculating the exact area underneath a curve? You guessed it, the width of each rectangle has to be the width of a single point. Instead of delta x, the width of each rectangle is dx from differential calculus. So each rectangle has to be just a point wide in order for there to be 0 area for each of these little top triangles, which I didn't bother to draw. And what that means is, if each rectangle is a point wide, in any given length of curve, there's an infinite number of rectangles if we want an exact solution. So in sigma notation, our equation for the summation of all the different rectangles is I equals 1 to infinity, because there are an infinite number of rectangles if we want the exact area. And incidentally, you might have guessed 0 for delta x, but notice we have to say dx, because we can't exactly say 0, because if we have 0 times the height of the rectangle, we would in fact get 0 area, and in 0 it won't give us a solution. So we have to say that the area is the summation of the height of each rectangle times just barely not zero, or dx. So what this notation means, if we have an infinite number of rectangles, and each rectangle is the width of a point wide, and the height of each rectangle is the function f of x at that position of x, and if we add them all up, we'll get the exact area underneath the curve. Notice the width of each triangle on the graph is going to be dx, and probably the height of each triangle on the graph is also going to be like dy, and the area of our error is going to be a single point of area. And so, in fact, the error of our graph, which was the amount of area in each of these little triangles, if each rectangle is only dx wide, we're going to have zero error for our computation of the area of the graph. Incidentally, a significant portion of a calculus class is spent on proving that it is possible to actually calculate an infinite sum of these, like there's an infinite different rectangles that we're adding up, and notice that each individual rectangle has a very small area in itself, because notice every width of rectangle is differentially small. This dx is such a small number, it's just the width of a point times a finite number. So in fact, this is an infinite sum of very small, tiny numbers, and a significant portion of calculus is proving that you can add up an infinite sum of infinitely small values, namely the area of each rectangle that's only a point wide. How much area can that be? But you can, if you have an infinity of them and add them together, you can get a finite, actual, real-world answer, which is kind of strange when you think about it. And incidentally, that was not the first time that such a problem had been asked, but it was the first time in the invention of calculus when this problem had been solved, as far as I know. Although, now that I think about it, I believe that Archimedes might have figured this out, and Archimedes might have been thinking about it because of Zeno's paradox, and you might have heard Zeno's paradox. And Zeno's paradox, one formulation of Zeno's paradox is this: if you were going to run in a foot race, in order to finish the race, you must first go half the distance of the race. And in order to go half the distance of the race, you must first go a quarter of the distance of the race. But in order to go a quarter of the distance of the race, you must first go an eighth of a distance of the race. And it doesn't take long before there's an infinite amount of distances that you must first go before you can finish a race. And therefore, since you cannot do an infinite amount of things in a finite amount of time, you can't even run a race. Right? That was Zeno's paradox. Isn't that interesting? It wasn't until the invention of integral calculus where we as a species have conclusively proven, well, fairly conclusively proven, because remember, most of calculus is based on a fallacy, that you can have an infinite sum of things be a result if the size of each individual thing is tiny, is infinitely small. So integral calculus does have this interesting idea that you can know the value of an infinite sum of things, an infinite number of rectangles, provided that each area of the rectangle is infinitely small. And so we've mathematically proven that in integral calculus, and have in fact resolved Zeno's paradox. Isn't that kind of interesting? I feel like that was a mystery that was with us for thousands of years, and we know the answer. It's possible to do an infinite number of things if each one of those things is infinitely small. And that's mathematically proven, if you believe calculus. So I encourage you in your calculus classes, when you have to learn this, and it's kind of, for me it was the tedious part of calculus, but that's what it's all about. It's actually answering Zeno's paradox, which has been a riddle for humans for thousands of years. Now, this sigma notation is good if you have summation of maybe several different objects. And it's really good if you have exactly 4 objects, because notice the sigma, Greek letter sigma, is written out of 4 lines. So if you have a finite number of things, say it's 4, sigma notation makes sense, like I equals 1 to I equals 4 here. But notice when you have an infinity of rectangles to add up, and in fact each rectangle is only a point wide, each of these things becomes a smooth function when it becomes the expression for the exact area underneath a curve. And so instead of using sigma equals I equals 1 to infinity to indicate that we're adding up an infinite number of little rectangles of area, we use this different notation. And this is the classic integral notation that you'll find in every calculus book. So instead of sigma equals I equals 1 to infinity, where we're adding up an infinite number of rectangles, we write this integral equation, and actually the integral equation is kind of a joke too. Remember I told you sigma was the Greek letter for S, and it meant sum. Well, here's the joke. The notation for integral, which is the notation that you're going to have to know as find the area underneath a curve, is this symbol. And 1, it's a single smooth symbol to indicate that it's a infinite sum of a smooth curve. And so it doesn't look like there's 4 discrete parts like it. It's singular and smooth. But also, it's just a tall letter S for sum. So it's kind of a pun, sort of. It's a pun. So, well, anyway, this is the integral sign, this, and there must be this dx. And what it stands for is an infinite sum of the areas of rectangles underneath a curve, where each rectangle is a point wide, and the height of each rectangle is the value of the function right there at this position x. But how you should think about it whenever you see this symbol is, oh, I want you to find the area under this curve f of x. That's what the symbol means. Let's take the equation, for instance, f of x equals x, the graph of which looks like a straight line that goes up to the right at a 45-degree angle. If you are asked to find the area of f of x equals x, it would be written as integral f of x dx or integral x dx. And generally in calculus, if this is the symbol that you get, integral x dx, it doesn't actually calculus doesn't expect you to find a numerical value for the area of x, but rather calculus expects you to find the equation for the area of f of x dx. So when you see this sort of calculus problem, it's asking you, tell me an equation for the area underneath the graph of x. I picked f of x equals x because this is one of the few equations for which I happen to know the area underneath the graph of f of x equals x. It turns out that the area underneath of f of x equals x, for any value of x, it's a triangle, and the width of the triangle is distance x, and the height of the triangle is also distance x. So for any value of x, it's always a triangle. The base of the triangle is value x, and for this particular equation, the height of the triangle is also x. And you might remember from geometry, the area of a triangle is 1/2 base times height, which in our case is 1/2 x times x, since for any value of x, the base of the triangle is x, and for this specific equation, f of x equals x, the height of the triangle is also x. So in fact, the area under this line is in fact 1/2 x squared. For any value of x here, the area of this little triangle here is 1/2 x squared. And if I pick a bigger x, the area will be there, the bigger x, 1/2 x squared, for any value of x. So for the specific case of f of x equals x, we can write an equation for the area underneath the curve, namely integral x dx equals 1/2 x squared. So notice the calculus problem is this. You get this is integral x dx, and what the question is, give me an equation for the area underneath the curve f of x equals x. That's this curve. And using geometry, I could know that the equation for this specific problem, integral f of x dx, is 1/2 x squared. And this equation will tell me the area of this triangle for any value of x that I want to plug into the equation. So, that is in fact the integral of x dx. There's only one other case where I know the equation of the area, and that's when f of x equals a constant. In this case, f of x equals 1, which is a horizontal line at y equals 1. And notice I know the area for any value of x here. It's a area of a rectangle at the base of which is x and the height of which is 1. So the integral of 1 dx is the area underneath this curved line for any given value of x, which is going to be x, whatever the x value is, times 1. So the integral of 1 dx is just x. And if you have f of x equals x squared, which looks like this, I'm just going to tell you the equation for the area. The integral of x squared dx, that's this area underneath this parabola, is x cubed over 3. That means if for any x I plug in on the x-axis, the area of that section of the graph here is going to be x cubed over 3. Notice there's an interesting pattern here. Remember that these symbols mean that find the area of just this function that's written right here. Now this dx here is just to indicate, to remind you what this is. This is an infinite sum of rectangles, but for all intents and purposes, the important part is the number in between the integral sign and the dx, because we're finding the area of this function. And look at it's got this nice sort of intriguing pattern. Integral of 1 dx equals x, integral of x equals x squared over 2, integral of x squared equals x cubed over 3. And it might help you to see this pattern a little more clearly if I write in a different way to write 1 dx. Because it turns out that x to the 0 power also equals 1. Actually, any number to the 0 power equals 1, so x to the 0 power equals 1. So instead of writing integral of 1 dx, I could as well write x to the 0 power, and that still equals x. But notice that x to the 1 power equals x squared over 2, and x to the 2nd power equals x cubed over 3. It's kind of a beautiful pattern, and I think you could guess what x to the 3rd power is going to be. What is the equation for x to the 3rd power based on this pattern? I find it somewhat intriguing that the equations for the areas underneath curves follow such pretty straightforward patterns. And isn't it sort of almost magical that the integral of x to the 3rd, that is in fact the area of x to the 3rd power, is in fact x to the 4th over 4. And so just based on patterns, if I tell you x to the any power is your function, it's pretty easy for you to tell me an equation for the area underneath that graph, and it's really kind of marvelous if you stop and think about it. For any power of x, you could know the equation for the area underneath its graph just by knowing this pattern. And so the pattern is, if you're given a function x to the any power n, and you want to know the equation for the area underneath that function, it's x to the n plus 1 power divided by n plus 1. Now, this is an important pattern. It's probably the most common integral that you'll take in AP Physics. But that's not actually why I picked this pattern. I picked this pattern because it suggests something about integration in general that's actually really important. The important thing about this particular pattern for integration is its relationship to the previous pattern for differentiation that we've already covered. Namely, they're kind of like inverse procedures. Like, if, for instance, if I have x to the n power and I want to find the integral, I add 1 to the power, and that's going to be the equation for the area of this. I have to divide by this n plus 1, but what I'm doing is I'm adding 1 to the power. But if I want to find the derivative or the slope, what I do is I subtract 1 from the power of x, and then I multiply by this n number. And that pattern, it suggests a curious relationship between the integral and the derivative. Namely, finding the integral of a function is, in a real sense, the opposite of finding the derivative of a function. Here's what I mean. So the problem of integral calculus is, given this, you have to find out what is the equation for the area underneath this function. So this is generally something that you don't know in integral calculus. So all the integral calculus problems is you're going to be given a function, and you want to find the equation for the area of that function. But notice, and this isn't just true for the power rule, is that this unknown equation, and we know the answer to this one, the area of x dx is x squared over 2. But the interesting thing about the derivative is the derivative of x squared over 2 is x, which is the function that we want to find the area of. And notice that in this case, the derivative of the area of x squared here, remember that the derivative of x cubed is 3x squared, and then there's this third, it cancels out the 3, leaving you just with x squared. The derivative of the area of the function is, in fact, the function itself. And you can see that the derivative of x to the 4th power is 4x cubed, and there's a 4 in the bottom, so the 4 goes away, leaving you just with x cubed. So that pattern holds, and it doesn't just hold with power rule. And if you think about it, when you take the derivative of nx to the plus 1, you get nx to the minus 1, canceling out this 1, leaving you n, and you plug in the n here, and it cancels out the n plus 1. Isn't that kind of interesting? I think that's cool. But in general, this is true. If you are trying to guess the equation for the area of a function, how you should go about doing it is do the following. Think of an equation so that some new equation. So I'm asking you, this is how the general sequence of integral calculus works. Somebody gives you this, and your task is to guess an equation this, such that the derivative of this guessed equation gives you this. And that's what you spend most of the time in the integral calculus class doing. It's different ways to guess this equation so that its derivative is in fact this. And it turns out that's really true about the relationship between the area of the function and the function itself. So that's really interesting. The equation for the area of the function, all of these, is some different function, but it's such that when you take the derivative of the area of the function, it gives you back the function itself. Incidentally, that idea is the fundamental theorem of calculus. It's so important that I'm going to write it out. So the fundamental theorem of calculus says that if you have an equation for the area of a function, the derivative of the equation of the area of the function is in fact the function itself. So isn't that strange? It's strange. You have an equation for the area of a function underneath the curve, and if you take its derivative, you get back the function itself. Now that's just kind of a strange concept, because the derivative, remember, is the slope of any given function. So if you have a function that's the area of another function, the slope of that area function is in fact the function itself. There's a fair amount of time spent in a calculus class proving that the fundamental theorem is true, but it's just such an intriguing concept that if you know the equation for the area of a function, the slope of that equation is the function itself. Isn't that strange? That's just a weird concept. And it's mathematically proven to be true as far as anything in calculus is possibly proven to be true. And of course, the second half of any first-year calculus class is integral calculus, and all that you do is in integral calculus is basically exploit the fundamental theorem of calculus to guess the equations for the areas of different functions. So whenever you see this problem, integral of f of x dx, all you have to do is, they're asking me to find the area of this function. And all you have to do is, well, I just need to come up with an equation, let's call it capital F of x, such that when I take its derivative, I'll get back this original given function that they tell me in the integral problem. And so that's why the theorem is fundamental. The fundamental theorem of calculus is that's how you find the equation for areas under curves. And by exploiting this fact is, well, if whatever this function is, all I need to do is guess some other equation such that when I take its derivative here, I'll get back the original equation in the problem. So for example, let's say you get this equation. All you have to do is, so this actual problem says, tell me an equation for the area underneath cosine of x. Right? Just tell me an equation for the area underneath cosine of x. And in order to exploit fundamental theorem of calculus, all you have to do is like, well, can I think of an equation that when I take the derivative of that equation, I get cosine of x? And sure enough, you can guess f of x, capital F of x, equals sine of x. That's the equation for the area underneath cosine of x, because the derivative of sine of x does in fact equal cosine of x. Now, for this reason, this process of finding the equation for the area is also called finding the antiderivative, just because the integral is opposite the derivative. But I want to point out an important loophole. So we said that the antiderivative, or the integral of cosine of x, is sine of x. And we know this because of the fundamental theorem of calculus, because the derivative of sine of x is in fact cosine of x. Therefore, according to the fundamental theorem of calculus, the equation for the area of cosine of x is in fact sine of x, and we know this because the derivative of sine of x is cosine of x, and so it's kind of like the opposite of a derivative, gets an equation that when you take its derivative, it gives you the original equation. That's kind of the opposite of a derivative. So sometimes that's called an antiderivative, but there's an important loophole that I must point out. True enough, the derivative of sine of x is in fact cosine of x, but the derivative of sine of x plus 42 is also equal to cosine of x, namely because the derivative of 42 is 0. So interestingly enough, the derivative of sine of x plus any number that doesn't have x in it, any constant, is also cosine of x. So in fact, finding the antiderivative, there's a lot of equations that when you take its derivative, you get cosine of x. It could be sine of x plus 1, sine of x plus 2, sine of x plus 104, or sine of x plus 42. And there's a bunch of equations that when you take their derivative, it gives you cosine of x. So in general, how we'll write the answer to this equation is what's called the antiderivative, and in fact what we'll have to write is the answer to this equation is in fact sine of x plus c, because the derivative of sine of x plus any number that's a constant will in fact give you cosine of x. And so a lot of times in calculus problems you'll say find the antiderivative, and what the antiderivative of cosine of x is sine of x plus c. That's what they mean when they say antiderivative. And that's just because, remember, fundamental theorem of calculus says any equation that when you take its derivative, it gives you back this original function. That is an equation for the area of the curve. And I'm going to tell you why it doesn't matter. It doesn't matter what this constant c is in the next video. So, to sum up, when you see this symbol, integral f of x dx, all that it means is find an equation for the area underneath the curve of f of x. And how you do this is you guess another equation so that when you take the derivative of the other equation, it gives you back f of x. And there's a little loophole that it could be that other equation could be plus any constant, and we're going to talk about it in the next video. But that's all there is to integral calculus, is finding an equation. This is the given function f of x. Finding an equation that when you take its derivative, it gives you back f of x. It turns out that that other equation is the equation for the area underneath the curve.